Here is the first example of putting it all together. So the last example, we looked at this polynomial function and we found the intercepts and asymptotes. So just to remind you, here was the factored version. Remember, this is y. This has nothing to do with derivatives. And we figured out that the x-intercept was x equals 9, and the y-intercept was x equals 1. So x equals 9, x equals 1. We plugged in 0 for x for the y-intercepts. So both of those equal 0. We found out the y-intercept was negative 27. Vertical asymptotes, because it's a polynomial function, there is no denominator, there is none. And horizontal asymptotes, same thing. Polynomial function, there's no denominator, so there is none. Now, if you have a graphing calculator, it's good to graph this just to make sure you're doing everything right. If you don't have a graphing calculator, go to Desmos. You can see here's my graph of the original function. Obvious that the x-intercepts are 1 and 9, and the y-intercept is way down here somewhere. I zoomed out, and that is negative 27. There's ways to find that. Just put y equals 0 as a value. You'll see negative 27. So far, we're in good shape. Next thing I want to do is all the calculus, the increasing, decreasing, concavity, min-max, points of inflection. So we're going to have to take the derivative. The derivative is easy, but I'm going to allow you to use Wolfram Alpha on all of this just to save time. Really what this is all about is doing all the other stuff and finding out what the calculus shows you. So my first derivative, you can see, is here. The second derivative is here. So first, second. Critical numbers are where the first derivative equals 0. So I'm going to look at this first derivative, find out where that equals 0, and that's obviously x equals 5. Done with that. Possible points of inflection are where the second derivative equals 0. And this one's a little strange. The second derivative equals negative 6, which means just that. The second derivative is always negative 6. Therefore, it never equals 0. Therefore, there are no possible points of inflection. So I'm going to go like right next to it. Points of inflection, well, there's no possible ones, then of course there is none. Next is the increasing, decreasing, mins and maxes. So for increasing and decreasing, you can use that first derivative chart, which we know is you take your critical number, which is x equals 5. Let me bring this first derivative over for my chart. So the critical number is x equals 5. I'm going to do a test value, y prime of 0, y prime of 7. If you plug 0 into the first derivative, you get a negative 6 times a negative 5, which is positive, which means it's increasing on negative infinity to 5. When you plug in 7, you'll get a negative 6 times a positive 2, which is negative, which means it's decreasing on that interval. Which also means increasing to decreasing means we have a maximum at 5, comma, whatever you get when you plug in 5 to the original function. Now use your calculator, or you can use the graph. I'm using the calculator right now, negative 27 plus 30 times 5 minus 3 times 25. I got 48. Now, if you look at the graph again, does it look like this is 48? Sort of does, way up here, and it definitely is a maximum. You can use the maximum calculator on your calculator to confirm that. There's no minimum. And that's what the graph also shows. So really quickly, I could have used the second derivative test here to do the mins and maxes first. This might save you some time, so it's worthwhile taking a look at this. So let me just undo everything that I just did here. And again, I can almost hear the groans out there, but it may save you some time in the long run if you follow this advice. So pretend I never did this. And you can try to find the mins and maxes first using the second derivative test. Remember, the second derivative test is you take your critical numbers, which we found to be x equals 5. And plug them into the second derivative. Now, the second derivative, if you recall, is just equal to -6. So if you plug your critical number into the second derivative, you'll get -6 because that's what it is. So a negative in the second derivative test means the critical number is a maximum. So this means maximum at x equals 5. And we already did 5 comma 48. So that's a maximum. There is no minimum. So now you can backtrack. For increasing and decreasing, if we set up our chart, we already know that 5 is a maximum. So for 5 to be a maximum, it's got to be increasing to decreasing. So backtracking, I can say it's increasing -infinity to 5 and decreasing from 5 to infinity. So that's the other way to do that. It's sometimes the second derivative test is a lot easier than trying to use the chart. So that's why that is to your advantage if you like it. If you don't, do it the first way. All right, so now the last thing I have to do is the concavity. And the concavity doesn't change. You take your possible points of inflection and use the second derivative chart. But there is no possible points of inflection. So I can't draw a line here because there's no point of inflection. So really what we're doing is we're doing this entire range, -infinity to +infinity. And you can use anything. The second derivative at, well, let's just say 5. I already did 5 and I figured out it's negative. It's always negative, which means this is concave down from -infinity to +infinity. Sorry about the mess. It's concave up, nowhere. Never concave up. If you look at the graph, you can see that it's always concave down. So that's that. Hopefully that wasn't too messy. Hopefully you understood it. The next example is going to be a more complicated example. It's going to be a rational function, and we'll get to that next.